Okay, thank you. Does that work? I don't think so. Oh, okay. Okay, thank you very much for the invitation to talk from the Royal Meteorological Society, and thank you very much to the previous speaker. I could have listened for another hour of that, so it's quite frustrating to have to go into my talk. But I guess this talk is aimed at people who might not be as familiar with African weather and might not have quite the same background as some of the experts that are sitting here today. So I'm going to go through kind of like a bit more of a sort of starter's guide to African weather. So I'll talk a little bit about convection and the general circulation and how that impacts on weather over Africa. And then I'm going to do a basic tour around the seasons, so talking about the West African monsoon, the short rains and the long rains in East Africa, the low-level westerlies, the influences of moisture over Central Africa, and then finishing up with the Southern African region as well, and talking about some of the interaction with the extratropics. I'll then go on to talk about how all of these different factors combine to provide challenges for our numerical weather prediction models, and I'll finish up with a kind of summary and conclusions. So I hope that this gives you a little bit of a flavour, and hopefully we'll set the scene for some of the other talks that will go on for the rest of this afternoon. So I thought I'd start with a picture of, this is yesterday's satellite image. This is a false colour RGB image, and it's a mix. It's from the MSG satellite, but it's a mixture of optical thickness and temperature. So it's showing in the very, very deep red, you can see the highest clouds, the deepest clouds as well. So they're very thick and they're very high. So those are basically mesoscale convective systems or kind of thunderstorms. And you can see that especially over the majority of the African continent at the moment, we're in December. So of course it's summertime in the southern hemisphere and wintertime in the northern hemisphere. And this is where the main area of convection is, and there seems to be quite a lot of activity down in South Africa as well. Whereas North Africa is mostly cloud-free. There's some cirrus, so this is cirrus over here, and the pink is pulling out where the dust is present over North Africa, which Peter Snippet should talk about later. So as you can see in that previous slide, the majority of Africa is dominated by these squalls or thunderstorms or MCSs or mesoscale convective systems, as they're known. And the main process of these mesoscale convective systems is, of course, it's not so dissimilar from what we have in terms of kind of what we would consider a thunderstorm in the UK, except at a much, much larger scale. So on the larger scale, they're kind of even some of them are very, very complex structures, but predominantly they still have a warm air updraft going into them, and they have a cool air downdraft coming out of them, as you would expect in most thunderstorms. And in the case of these mesoscale convective systems, this cold air downdraft can be very powerful and hit the ground as a kind of in a radial form and then start spreading out. It can spread hundreds of kilometers away from the storm. And quite often this is referred to as a cold pool, or it can be referred to as a gust front, the kind of leading edge of that cold pool. And of course, this cold air downdraft, when it hits the ground, has a lot of hazards associated with it. So here are just some of the hazards that are associated with the squalls or thunderstorms in Africa. The first one along the lines of looking at the cold pool is, of course, as that cold pool spreads outwards, there's lots of strong gusty winds at the leading edge of it, so it can be a relatively calm day, and then all of a sudden it gets very, very windy at the front of that cold pool. And then also there's a strong shear zone. Because the cold pool is very dense, it means that it spreads out along the ground, so if a taking off aircraft might experience quite a lot, or a landing aircraft in particular, could have very, very calm conditions and then suddenly get into a very strong shear zone and have a sudden wind increase. As well as that, you also have lightning. So lightning's happening from cloud to cloud and cloud to ground lightning. And then finally is an intense rain. So you have a lot of flash flooding. And the rain values can be very much higher than we'd expect here in the UK. So quite often it can be up to 100 millimeters in a few hours. The other one is for aviation hazards, is the outflow region. So at the upper levels, you have very strong outflows, entrainment and detrainment from the cloud. So having a look, and this was mentioned in the first discussion that Bruce was talking about, is the diurnal cycle. The diurnal cycle is really dominant in Africa. They don't have so many kind of big geostrophic influences on the weather, so there's not the kind of big pressure gradients that you'd expect in the extratropics. So really, it's very, very dominated by solar heating. And solar heating, of course, there's lots of heating during the day and less so at night. So these are just two pictures, two kind of plots. On the left-hand side is a plot of the diurnal cycle of cold clouds. So this is cloud that is less than about 220 Kelvin as a percentage, and this is composed from GridSat data, which is a infrared data set made up of MSG and satellite data. And this is just for July, August, September in 2005. And on the right-hand side is the diurnal cycle of lightning strikes using the Met Office's ATDNet remotely sensed lightning data, which is again for July, August, September well, it's 2010, so it's a different year. It's not quite matching up. But I think the thing that you can really see here that in the afternoon and the late evening, so between 12 UTC and 21 UTC, these haven't been corrected for local time, so we are seeing real time here, but of course the meridian goes through this picture, so it roughly lines up. You can almost see the sun moving across the continent and warming up those storms and those storms bubbling up behind it. And of course the lightning is active at the same time as the storms are active as well. Interesting enough, with the lightning picture, you can see the real contrast in lightning over land compared to lightning over ocean. And then, of course, at night time, once the sun's gone down, so between 0 and 9, there's a bit of a lag because there's still energy in the system. But those storm systems really start to peter out. And this is a very, very strong cycle, and it's the dominant impact on weather. And that's why when Bruce showed the examples of a weather station in Bamako, you could really see that it was the dominant thing that was influencing the sort of long-term records was still this diurnal cycle. So let's have a little look more at the general circulation. So going on to how the circulation changes through the seasons. This picture here is the annual cycle of average precipitation over Africa, and it's taken from a 12-year mean of GPCP data. GPCP data is a satellite plus station data, so it uses gauge data as well as satellite data. And what you can see here is that from January through to kind of February, March, the ITCZ, the main area of convection, is located in the southern part of the African continent, and it moves upwards in March, April, May, going northwards as the sun goes northwards. Now, the interesting thing that's happening in March, April, May is that you get a very large amount of convection over that Gulf of Guinea region, and that's where you get a very strong ITCZ over the ocean. In June, July, August is the period of the kind of onset of the African monsoon, the West African monsoon, and you can really see the strength of the convection, especially in July and August, over the Sahelian region of West Africa, which is normally very arid. By September and October, that monsoon starts to retreat southwards again, and you can see the contrast between the picture in October and the picture in May in terms of where the convection is located. In May, it's located far more over the ocean, and in October, after it's retreating, it's located far more over the land. By November and December, the ITCZ has moved back down to its most southern position and is located over the southern part of Africa. So, what's the interesting picture here? Well, the interesting picture is that a lot of the convection is focused over continental regions and not so much over the ocean. And the only time that the ITCZ is very present over the ocean is that kind of April, May time, when you seem to have a lot of convection happening in the Gulf of Guinea. So what's the story with this? Well, we can link it up very happily with the annual cycle of sea surface temperatures off the coast of Africa. So this is just a picture of the annual cycle of sea surface temperatures in the Gulf of Guinea and the South Atlantic, and this is taken from the 30-year mean of Ostia sea surface temperature data. Ostia is a data set that's maintained by the Hadley Centre at the Met Office, and it includes satellite plus buoy data, so it's in situ data. And what you can see here is that from the 30-year mean really shows that in March, April, May is when you have your warmest sea surface temperatures over the Atlantic Ocean and near the equator. And by June, July, August, you get the formation of a cold tongue or a cold area of upwelling that forms along the equator. And it's this area of cold that's still retreating in sort of September, October, November, which means that you don't have as much convection over the ocean as you do when the ITCZ is moving northwards. So in other words, the ITCZ northwards is not quite the same as the path that it follows southwards. So let's do a tour around those seasons and go a little bit further into the meteorology of it. So the West African monsoon, some people might recognize this. This is you're sort of floating, if you like, in this image over the Atlantic Ocean and looking down at Africa. You're looking eastwards. So the Sahel's in the middle with the Sahara to the north and the Guinea coast to the south. There's a few papers there if people want to read up more about the processes for West African monsoon. Many of these ideas have basically come from papers that came out of AMA. But at the beginning of the season, you have convection in the ITCZ based around the Guinea coastal region. So that's kind of Ghana, Nigeria, and Ivory Coast. And then, of course, this doesn't show this in the picture, but of course it extends into the Gulf of Guinea as well. And you have convergence at the surface and divergence aloft. And you can see there the red arrow is kind of indicating that there's mainly northeasterlies or northerlies over the majority of the Sahelian region, and as was mentioned before, these are sometimes called the Harmattan winds. Now what happens is, as the sun moves northwards, the Sahara starts to get hotter, and as it gets hotter, you have low pressure at the surface. You have air rising, and that then means low pressure at the surface. At the same time, you have this cold tongue developing by the equator, and that means that the forces, the geostrophic forces that are on the large-scale flow change quite suddenly, and you have this kind of jump of the monsoon rains northwards, and you have a resetting of the circulation. So instead of having a kind of the sort of normal ITCZ circulation, you have a bit more of a complex circulation with lots of moisture being supplied into the Sahel region. So on the larger scale, this kind of looks something like this, where you have a kind of southwesterlies and even westerlies coming into the Sahel region supplying moisture, and this is known as the monsoon inflow. And then above this, at 600 hectopascals, you have the return flow, which is the African easterly jet. And this jet, of course, because it's easterly, is unstable barotropically, and that means that any perturbations on the jet are able to grow because it's an unstable jet. And as those perturbations grow, they form vorticity anomalies, and those vorticity anomalies that then travel westwards are known as African easterly waves, and these tend to show themselves at about 700 hectopascals in the southern part of West Africa and 850 hectopascals in the northern part of West Africa. And the thing that's significant about African easterly waves is that they tend to modulate rainfall. So I'll show you that in the next plot. And then aloft, if people are really fans of the higher latitudes, is the tropical easterly jet, which I won't talk about today. So African easterly waves, why are they interesting? Well, I love this picture. This is a satellite image, I think, taken from the 23rd of August 2010. And what it shows is this was a particularly active time for African easterly waves. The image is an RGB, so it's a false color RGB of kind of combining visible and infrared data. So the very kind of white top, blue top clouds are very, very high clouds. And you can see over most of West Africa, there's actually these two very large mesoscale convective systems that are dominating the weather. And you can see in the Atlantic, there's these other mesoscale convective systems that have actually reformed into tropical cyclones. And that's, tropical cyclones are often initiated and started from African easterly wave disturbances. And in this particular image, you can see that some of those systems have recurved, and they've recurved, and they're even affecting weather over Europe as well. All these tropical cyclones, of course, go into the Atlantic and affect the Caribbean and America. So I think just a kind of cartoon impression of where your African easterly wave might be, that's basically along the lines of you get convection mainly in the positive vorticity parts of the wave, and a suppression of convection in the negative vorticity parts of the wave. So showing that in a little bit more of a case study, this is from another time, this is in 2013, and this is just a series of, actually I think this is ECMWF data on the right-hand side, of V winds which are shaded. I've just, so you don't have to agonize over the plot too much, I've shown where the trough is of the African easterly wave, so where the V winds are switching from southerlies to northerlies. And you can see that over that period, which is just a day, that the trough of the African easterly wave is moving from the east to the west. And at this time, in the first part of the trough, when it's towards the eastern part of the domain, convection tends to initiate at or behind the trough axis. This is generally because that's the area of the southerlies where you might have more moisture present. As the trough moves forward, then convection sometimes tends to move ahead of the trough. So actually, if you're looking towards the more western part of West Africa, then you might find your convection ahead of the trough rather than subsequent with it. Okay, so moving on, what happens in the next season? Of course, in October, November, December, you've got a very cool and moist area in the northern part of Africa, which is kind of after the monsoon, and the monsoon is now starting to retreat. And at the same time, you've got a very hot and dry Namibian desert, and it hasn't rained there for 6 months. So what you tend to have then is it sets up a circulation where you have low-level westerlies at about 950 hectopascals to 850 hectopascals, depending on the orography in that region. And that's actually also the time of the African easterly jet, the southern component, or sometimes called AEJ south at 600 hectopascals. And the African easterly jet in the southern component is only present one season. It's only present in OND. The other kind of influence on weather at this time of year is the Somali jet. So the Somali jet's at about 850 hectopascals, and that jet is associated with the kind of large-scale pressure differences between the northern hemisphere and the southern hemisphere, and it has a relation also to the Indian monsoon. So all of these kind of weather influences add up to there's two different seasons in East Africa. I have to admit, I don't know why they're referred to as the short rains and long rains, but these are the characteristics of the two seasons. So you can see that in the long rains, which is March, April, May, this is when the IPCZ is moving northwards, and at this time you get a very, very strong precipitation, especially around the Lake Victoria region, and quite a lot of strong precipitation around the sort of coast of Tanzania, and most of Kenya, Tanzania, Ethiopia, and GLC will receive a lot of rainfall all at the same time. Whereas the short rains, interestingly enough, I don't know why they're called the short rains, because to me they seem to last a little bit longer, but they go from September through to December. It depends on which country you're in as to when exactly they hit. But certainly the season's probably not as strong in terms of the amount of rainfall that they receive, but it potentially lasts a little bit longer. Especially over Lake Victoria, you can see the contrast there between the November, where it's getting sort of a certain amount of rain compared to April. And in the center of this image, you can see just a annual cycle of the mean daily precipitation for Lake Victoria. So you can see there that there's during the long rains, this is when they receive most of their rain, but then they have this longer rainy season from September through to December, January. So going on to Central Africa, which is the other coast, the low-level westerlies are very influential on the amount of moisture and the amount of convection that is then initiated in kind of October time. Wilfred Pockham from Cameroon has recently published a paper on this in Journal of Climate, which I very much encourage you to look up. So as the monsoon is retreating from West Africa, the center of convective heating moves over the equator. This means that you've got a lot of kind of convection, lots of latent heating, which is being generated by that convection, which basically leads to a pressure gradient from the over the ocean compared to the land. And this means that you're then pulling in even more air into the system and pulling more moisture into the system as well. And these are creating these kind of low-level westerlies, which you can see in reanalysis as well as in observations. So moving finally on to Southern Africa. Am I doing okay for time? Yeah, okay. So the last one is Southern Africa. So I know there's a few people on WebEx listening from South Africa, so I do apologize. You know I'm not an expert in South African weather, but I've tried my best here. There are lots of synoptic influences in Southern Africa, and I think the thing that makes it potentially the most exciting place to study is that it's the real area where you have interaction of the extratropics with the tropics. So just here in this image, you can see that there's on the left there's a satellite image, which is a viz image from satellite, just showing that there's lots and lots of tropical convection over the sort of mainland kind of tropical region of Africa. But you can also see some of the extratropical larger scale pressure systems that we sort of expect in the mid-latitudes much further to the south of that image. And on the right-hand side is the synoptic chart at the same time that this image was taken from the South African Weather Service. And they've marked on where the lows and the highs are, where the synoptic pressure systems are. And there's, at the bottom, of just below that, you can see the water vapor image that's all happening at the same time. So I think the point is that in this particular image, you've got a low trough that's pushing south, initiating convection within the tropical region. And at the same time, you've got synoptic weather systems which are influencing from the south. So South Africa has a very kind of complex weather situation, which makes it very difficult to, it has lots and lots of influences on its weather. So going into that a little bit more, South Africa is affected by extratropical synoptic high and low pressure systems much more than anywhere else in Africa. Most of Africa is experiencing a much more kind of slack pressure gradient, and these pressure systems that we're talked so much about in the mid-latitudes are not quite so relevant, but they are more relevant for the southern tip of Africa. It's also, however, impacted by kind of tropical localized convection as well. So these kind of things sometimes interact with each other. And here in this diagram, you can see I've put on a kind of cartoon of where the extratropical synoptic systems might have a little bit of influence. And at the same time, if you tend to have a situation where you might have some diabatic heating that might either be coming from the ground or from thunderstorm development in this region, then you might get a tropical low pressure developing over kind of more sort of northern part of southern Africa. And when if you do get a situation where you have a tropical low developing over the northern part of southern Africa, it's able to then interact with some of the extratropical lows that are off the coast of southern Africa. And sometimes this can result in a situation where you have almost like a joining up of these two areas of low pressure. And this is sometimes referred to as a tropical temperate trough. So it's the idea that your tropics and your temperate areas are interacting with each other and creating weather. This is particularly kind of notorious in South Africa, as it's known as one of the times when you get kind of the most severe convection, especially over the eastern part of South Africa. So, challenges for models. I hope that's a kind of relatively whirlwind tour of what's important for African meteorology. I realize it's quite hard to maybe take everything in one sitting, but I think that at least it's maybe given us some food for thought about why it might be difficult to weather forecast in Africa. So I've probably been a bit kind of, this is my point of view here, but I think these are the challenges for what we have to deal with in terms of weather forecasting, and especially for numerical weather forecasting. The first one is process representation. As I've kind of talked about before, Africa is hugely dominated by convection and small-scale processes. So unlike in the mid-latitudes, where we can rely a lot more on our kind of big, large-scale shallow water equations, we're having to rely a lot more on small-scale processes and parameterizations. So things like convections, cloud radiation, land surface, aerosols, orography. I have to say, there's not very many papers on orography over Africa, and the influences of mountain meteorology for Africa is very, very, there's nothing. So if anybody wants to study that, then I think there's a big gap in the market. Extratropical interactions, coast, rivers, and lakes. I haven't even talked about Lake Victoria, but it has a fascinating meteorological system around some of the big lakes in Africa. And of course, the deserts and rainforests. So a lot of these kind of features are very, very small scale, but have big scale influences. And as you've been seeing in those satellite images, some of those small scale storms can develop into very, very large mesoscale systems that can influence on a very big scale and cause a lot of destruction and a lot of problems for people who live in Africa. The second one is predictability. So of course, there's as most meteorologists in the mid-latitudes will know, it's much easier to forecast where a big weather front is going rather than thinking about where one individual storm is going, and that's a big issue about the predictability of convectively based weather. The other one is kind of these few synoptic influences, so a lot of the models depend on kind of big dynamical equations, and they are maybe not as good at representing things on the small scale, and that's something that's a big challenge for us. And then the other thing is that weather is present on scales of hours rather than days, so it's not, you don't get persistence over many, many days. It might be one difference from one day to the next. I think the other thing is that really thinking about on a seasonal time scale in terms of the amount of seasonal forecast, the seasonal rainfall that you receive, often it's very small scale storm systems that can make a big difference to how much rainfall you get on a seasonal time scale. So for example, in West Africa, in some areas of the Sahel, they might only receive 5 or 6 systems in their particular location, so 5 or 6 storm systems in a whole season, but that's their whole season's worth of rainfall. So if you don't get your models to a point where they are able to represent convection on those seasonal timescales as well, then it's very difficult to predict on a seasonal timescale how much rainfall is going to fall. And the final thing I'm going to touch on, which I guess has already been a bit of a theme, is evaluation. So finding out what the truth is. One of the really big challenges that we have for developing models over Africa is that there's not very many in situ data sets, or that many of them don't actually get onto the global telecommunication system and aren't shared externally. So it's very hard for us to test how good our models are performing because we don't know what the truth is. So we have to be quite inventive, and a lot of the kind of evaluation of models relies very heavily on satellites and gridded data sets. So there's a really good community around the world that is working on those, but it's probably not as good coverage over Africa as we would like it to be, and the uncertainty in those data sets, the uncertainty in observations is very, very high. So then I'm going to do a bit of this is my pitch, I guess. So I'm co-chairing a big initiative that the Met Office runs called the Africa Process Evaluation Group. And in this group, we try to make sure that all of the cutting-edge science that people are doing at universities is being pulled through to model development and improving our models over Africa. So feeding into this model development is kind of research, and then on the other side is the operational side of things. So we spend a lot of time talking to forecasters in Africa as well as in the Global Guidance Unit at the Met Office to see what are the main problems and how should we address them. So we really rely on having partners for this. So one is our academic partners that we have around the UK. Of course, we have people from across the Met Office in different areas. And finally, it's the African Met Services, which have really started to come in and help us with this. So just a summary, so you're standing up. So African weather is dominated by tropical convection, which has a strong diurnal cycle. The ITCZ moves northwards and southwards of the season and brings the rainy season to different parts of Africa. The models must represent processes on fine scales, and evaluation is a really big challenge. And the African Process Evaluation Group is a UK initiative to bring together scientists working on models for Africa. Thank you very much.
Thank you very much, Caroline. Questions, comments?